impact the U.S. winter weather. I talked in my last video about El Nino and the North Atlantic Oscillation. I talked about El Nino separate and NAO separate, some of their impacts, whether we're in the El Nino plus the positive phase of the NAO versus the El Nino and the negative phase of the NAO. I did that in my last video. And now we're going to continue to keep the theme out in the Pacific Ocean, specifically the equatorial Pacific Ocean. And in this video, I'm going to talk about the MJO, or the Madden-Julian Oscillation, and U.S. winter weather. This is a great example here on the title slide in the presentation tonight, showing the many different impacts of various phases of the MJO across this equatorial Pacific area. Now, anytime you see the darker green coloring, that indicates wetter than normal conditions. Whenever you see the brown shading, that indicates drier than normal conditions. And so what happens with the MJO, and I'll get more into this throughout the slides in this presentation, in this particular example, I'm showing you where the enhanced rainfall is located by this darker green area here in the Western Pacific Ocean. This particular MJO phase is phase 6. And there could be many various impacts downstream of what goes on in this equatorial tropical area. Above this particular dark green area, we have rising vertical air motion. Above this particular brown shading, drier than normal condition area, we have sinking vertical air motion. And then you see the purple arrow here and showing you how the storm track is diverted across the eastern North Pacific Ocean. And so there's many downstream effects of this convection, the enhanced convection and rainfall activity in the tropics, and where these enhanced areas of rainfall set up versus the drier areas set up across the equatorial areas of the Pacific Ocean. And that's exactly what we're going to take a look at tonight in this presentation. So my overview to kick things off in tonight's video, I'm going to examine the Madden-Julian Oscillation, the MJO, and its impact on the U.S. winter weather. We will look at the definition of the MJO, and then we'll also take a look at the MJO behavior in relation to the El Nino Southern Oscillation, the ENSO. And then finally, we'll examine past U.S. winter temperature anomalies for various MJO phases. I'm really going to focus in on those winter temperature anomalies mainly. I also will mention briefly about precipitation anomalies, but really my focus in tonight's video will be on the U.S. winter temperature anomalies. First things first, as we get started this evening, let's go ahead and define the Madden-Julian Oscillation, or the MJO. And basically what it is, it's an intra-seasonal fluctuation, or a wave, occurring in the global tropics. And the importance of this wave or intraseasonal fluctuation, it does result in variations in several important atmospheric and oceanic parameters, including the lower as well as the upper level wind speeds and directions, the cloudiness areas, enhanced rainfall, sea surface temperatures, and ocean surface evaporation rates. So all of these variables, specifically the vertical motion, the air motion, really does have global reaching impacts. What is the MJO specifically? When I say a coupled ocean atmosphere system, basically we're involving a system that interconnects the ocean with the overlying atmosphere. And it usually is on a typically a 30 to 60 day length for the MJO. And importantly for us here in the United States is it modulates the weather. It can modulate the tropical cyclones, the amount of activity in specific ocean basins. It can modify the extreme temperature and precipitation. It can definitely modify your storm tracks depending on what phase of the MJO you are in, as well as the atmospheric blocking events where those upper level ridges really set up across the northern hemisphere. The atmospheric rivers. And what is an atmospheric river? It's an area of extremely copious amounts of moisture that typically works its way from the tropical Pacific towards the west coast of the United States. It can result in some extreme flooding cases when you see atmospheric rivers pointed towards the U.S. West Coast. It also can impact the tornadoes, where they form, the general favorable areas for severe thunderstorms, which breed the tornadoes, and then also impacts weather in the Arctic, believe it or not, as well as the Antarctic. So that's why we're going to talk about the MJO tonight. It has far-reaching impacts. And basically what the MJO is, it's an atmospheric response to tropical diabatic heating. Diabatic heating generally referring to those warmer ocean surfaces, the warmer than normal sea surface temperature anomalies, and then the interaction with the extratropical variability, specifically other teleconnections. And before we get to some graphics here, I'll kind of explain and break this down. We have to go through a few more bullets here. The MJO is characterized by an eastward propagation. And generally, on average, that eastward propagation of the enhanced rainfall area is on the order of 4 to 8 meters per second. Again, it has an enhanced rainfall area in the tropical areas of the Pacific, but also has a suppressed area where the air's sinking. And it generally forms over the Indian Ocean and the Pacific Oceans. That's usually the areas that usually it forms the Indian Ocean and works its way from west to east. It works its way into the western and sometimes the central Pacific Oceans. Along with the variations in tropical rainfall with the MJO, the upper and lower atmospheric circulation anomaly features occur in the tropics and subtropics, and this results in some changes, some big changes in storm tracks, for example. Again, those temperature anomalies, extreme weather events, and where they form and extend around the globe. Now, these anomalous features provide important information on ascending or rising vertical air motion and descending or sinking vertical air motion associated with various MJO phases, and I'll get more into that here in a moment. And overall, that tropical convection leads to poleward and eastward Rossby wave train extensions into the middle latitudes. So you get these wave-like features that set up and into the middle latitudes, and that has major impacts on who gets wet, who gets cold, who gets dry, and who gets warm. Here is an example of the MJO, generally showing you this enhanced area convection or this enhanced area of rainfall here in the top left diagram. I kind of break down what each of these arrows and the coloring means here. This is a vertical cross section, by the way, each of these examples of the MJO wave as it propagates generally from the west towards the east, from the Indian Ocean. In the top example here, you notice how this convection, enhanced precipitation, enhanced rainfall is over the Indian Ocean initially. This is showing us at day 0, okay? And these red arrows generally indicate the wind direction. So initially I got low-level converging air, right? See these arrows, these bottom arrows pointing towards each other. As air converges, it has nowhere to go but up in the atmosphere. And as the air rises, it cools, it condenses, it forms clouds and precipitation. And at the top of the cloud, with this enhanced convection area or enhanced tropical rainfall area, we have diverging air streams. See how these red arrows at the top of the cloud are diverging or spreading apart from each other. And so this is a general circulation of what goes on. The red sea surface temperature indication here, that arrow, that indicates positive anomalies. Whenever you see the blue down arrow here, the blue coloring for SST, sea surface temperature, that indicates cooler waters or negative anomalies. And these MJO waves, as they propagate from west to east, generally redistribute mass around the global tropics. And again, I kind of hinted at the vertical air motions that occur ahead of and behind this enhanced convection or enhanced rainfall area. So again, starting off in the upper graphic here, okay, the top one, we have enhanced convection, rainfall over the Indian Ocean. It propagates to the east. And out ahead of that enhanced convection, by the way, you see where the sun icon is? Generally, we have sinking air motion at this point, okay? And then that enhanced convection or enhanced rainfall area continues to propagate eastward. Now, by day 10, it's over Indonesia. And ahead of it, we have, again, that suppressed area where air's sinking out ahead of this MJO wave. And then back behind it, we have what's known as suppressed convection as well in sinking air motion. So you see we got downward vertical motion right here ahead of the MJO wave. We have upward vertical motion within this cloud, and then we have downward vertical motion after the MJO wave passes. And then finally here at day, let's see, this is day 30, you see where this enhanced convection or enhanced tropical rainfall is located. It's now over the Pacific Ocean. And we have suppressed air or suppressed convection and sinking air motion where the sun is behind this passing MJO wave. By the way, this figure was adopted from Madden and Julian, who discovered this phenomenon. This is from 1971-72, right here, this graphic, and what they devised and how they envision things. Here is the wave propagation, this dark arrow at the top, by the way, propagating from basically from the west towards the east in the deep tropics. All right, so a couple more tidbits about the Madden-Julian oscillation, or MJO. The dynamical models, they generally do a poor job in MJO prediction, where the enhanced rainfall or convection is going to end up. And this is mainly, when you're talking about dynamical models, it's because of the inherent difficulties they have in discerning tropical convective scale processes. All right. Basically, these type of dynamical models feature these subgrid scale parameterizations. Now, I know it's a fancy little wording here, but what this means is that they're too coarse. They can't pick up on the finer detail processes, including that tropical convection or enhanced rainfall in those tropical Pacific areas. So the dynamical models do a fairly poor job in the MJO prediction over time. Satellite data is generally going to be used to determine where these areas of strong convection, where they occur, the enhanced rainfall, and how these areas depart from the long-term norm. Radiosondes, which are instruments which contain basically launching radiosondes. It's a vertical profile of the atmosphere at various locations. And with the radiosonde instrumentation, you're going to get as the weather balloon rises and the radiosonde is attached to the neck of the balloon, it's going to transmit certain weather information back to the ground, including your upper level winds at the various vertical levels. As a weather balloon ascends, that radiosonde is going to ascend with it. Okay, so you're going to get temperature with height, wind direction, and speed with height. You're going to get the humidity, amount of moisture with height, stuff like that. So these radiosondes, which are again attached to the neck of these weather balloons, which are launched regularly, giving us the vertical soundings, they provide crucial information on the atmospheric winds, like I mentioned, the temperatures with height, moisture, and pressure at many levels. Other tools to identify the Madden-Julian oscillation. Now, there's other tools out there. I'm not going to get too in-depth on this tonight, but you can actually look at outgoing long-wave radiation. That's abbreviated OLR. You can look at the velocity potential, which is a measure of the divergence in the upper atmosphere. Okay. When I talked about upper level divergence, I'm talking about at the top of this enhanced convection, this cloud. See how these red arrows spread apart in every case here of this diagram from the top to the bottom? That is upper level divergence when the air spreads apart. So we can look at the velocity potential, we can look at upper and lower level wind anomalies, as far as your where your areas of converging air and diverging air are occurring. And then we can look at the 500 millibar, 18,000 foot height anomalies to analyze how the MJO is actually impacting the middle latitudes. Here's some great diagrams now that will hopefully help you understand what MJO is a little bit better. All right, so this is an example where the equatorial Pacific, we're going, in this particular diagram on the left, I'm going from the central Pacific around the international date line, working our way west towards the western North Pacific around the Philippines, the East China Sea, South China Sea area, and then also working our way west towards the Indian Ocean. In this particular example, we have this deep green arrow pointing upward that indicates rising air motion. Whenever the air rises in the atmosphere, again, it results in cooling, condensation, the formation of clouds, and ultimately rainfall over time. Once this cloud grows tall enough, it's going to precipitate out at the base of the cloud towards the surface. So we have this low-level converging air, the low-level, see this low-level convergence? See the green arrows here closer to the surface, the ocean surface? Actually, that'd be, we're at 850 millibars, 5,000 feet above the ocean, but regardless, we're having converging air motion when these two arrows are pointing towards each other, then upward vertical motion through the atmospheric column. And then we have, see how these green arrows at the top of the cloud spread apart? That's our diverging air or divergence aloft up to about 200 millibar level. That's about 40,000 feet above the ground. So this is our enhanced convection area here, or enhanced tropical rainfall. Happens to be over the Indian Ocean in this example. Notice there's an eastward movement here to this particular enhanced convection area or enhanced rainfall area. So movement towards the east, and then ahead of that enhanced convection area in the Indian Ocean, in this example, we have this darker brown arrow indicating downward motion. So we have downward vertical motion, and now at the top of this area, 200 millibars or 40,000 feet, we have converging air. The air is coming together. It's going, once this air meets, it's going to basically work its way downward in the vertical direction and then spread out and resulting in this horizontal divergence closer to the ocean surface. This is going to result in that suppressed convection area, okay? So this is going to be a dry area ahead of this MJO wave. So all this up and down motion in the tropical areas of the Indian Ocean and the Pacific Ocean can have some impacts further downstream where we live in the United States. Now look over here on the right, I'm showing you the various phases of the MJO. So the Madden-Julian oscillation is divided up into 8 phases total, ranging from phase 1 all the way to phase 8. And what these dark numbers indicate is where the enhanced rainfall is going to set up, or enhanced convection. So if I'm in MJO phase 2, for example, my convection or enhanced rainfall will be located over the Indian Ocean. If I get to phases 4 and 5 of the MJO, now my enhanced convection is going to be located over what's known as the Maritime Continent, or Australia. As I work my way now towards the east, if I work my way towards phases 7 and 8, now my convection is over the Western Pacific, inching closer, much closer to the 180-degree longitude line here at phase 8, which is the international date line. So 8 phases of the MJO. Keep that in mind as we move forward. This is just an example of all the global impacts the MJO can have on the weather. Not just for the United States winter. It also can have impacts on the monsoons, the northeast and southwest monsoons. It results in sinking air motion over Indonesia typically. When we get, like, for example, some of the El Nino conditions kind of work with this. So you kind of see there's a lot of different things here, okay? So the storm track up here in the eastern North Pacific can be shifted. There's your atmospheric rivers pointed towards the western coast of the United States. You've got, tornadoes in the southern U.S. there and Dixie Alley. You got hurricanes impacted by the MJO as well. So there's a lot of, you can see the key here at the bottom here, the legend here and what it means. This is courtesy of NOAA. But there's a lot of different impacts. Hurricanes, like storm tracks in the winter season, where the extreme heat and the cold set up. So that's why we pay attention to the MJO. Now, the MJO phases are going to equate to different outcomes throughout the course of the year, okay? For example, phase 1, if I'm in MJO phase 1, that will indicate colder than normal temps for the eastern United States during the heart of winter. However, if I looked at that same MJO phase 1, that's going to indicate milder than normal temperatures for the same region in October. They're not going to be nearly as cold as they would be in, let's say, January. During the winter time, just to let you know, the colder phases for the eastern United States, colder temperatures, are going to be associated with MJO phases 8, 1, and 2, while the mildest phases in the wintertime for the eastern U.S. are going to occur in phases 4, 5, and 6. And I'm going to show you plenty of examples of the temperature anomalies and what the MJO was doing on various times of the year, specifically the winter. Now, as far as the MJO activity in relation to the El Nino Southern Oscillation, the ENSO, generally, research has found, Roundy et al. In 2010 wrote a research paper and discovered that stronger MJO activity typically occurs during La Nina winters. Now, we just came out of La Nina winter this past winter. We had 3 consecutive La Nina winters, okay? And typically, you get stronger MJO activity from their research. That's what they discovered, Roundy et al. They typically found that stronger MJO activity occurred during La Nina winters, okay? Important thing to keep in mind, while weak or absent MJO activity occurs during strong El Nino events. Now, this is important for us, okay? because we're right now the climate models are forecasting a strong El Nino at a pretty much a guarantee at this point, it seems like. So if we have a strong El Nino event this fall and specifically winter season, their research indicated that weak or absent MJO activity occurs during strong El Nino. So maybe MJO won't be as much of a factor this winter is what I'm getting at. Now, this is showing you examples, this graphic here, courtesy of NOAA. This data actually is from Arcodia et al. In 2020. All right, so we're looking at the MJO and the El Nino and its influence on precipitation patterns here. Okay, in the MJO, particular phases 6 and 7, you get see where the box is in all these diagrams? You see this box. So the Gulf Coast brown means drier than normal. So MJO phases 6 and 7 generally equate to drier than normal conditions. I believe this is winter time. And then you look at the MJO in phases 8 and 1 here, and it's usually much above normal for that same area in the box here along the Gulf Coast and the southeast. See this? See the difference here? MJO phases 6 and 7 drier than normal, phases 8 and 1 much wetter than normal during the winter season. Now, if we look at La Nina alone and what we'd expect this light brown or tan shading below normal precip for the same area, the Gulf Coast, Florida, generally Georgia, Alabama, Mississippi. And look at La Nina here as well. Generally below normal once again. Bottom line is, if we just look at this thing across, let's go horizontally across now and examine this. The effects of MJO phases 6 and 7, drier than normal Gulf Coast and the southeast. If I throw La Nina in there, guess what? That also typically has drier than normal conditions in that same area. If I combine MJO and La Nina, they're working together in the same direction. That's known as constructive interference or amplification of these two teleconnections. And here's a combined effect. Well below normal precipitation in this box along the Gulf Coast from New Orleans to Mobile, right over to Tallahassee. Look at this. Now, if I take the MJO phase 8 and 1, which I'd expect wetter than normal conditions in this area, the Gulf Coast, Mississippi, Alabama, Georgia, and then I combine the effects of La Nina. Now, La Nina would generally indicate drier than normal conditions in this box. So, wetter than normal in MJO phases 8 and 1 for this area, drier than normal in a La Nina winter. If I have these two things going for me, then look at the combined effect. The MJO phases 8 and 1 actually win out in this case. But this is a case where we have two teleconnections working in the opposite direction, and this is known as destructive interference. This MJO phase 8 and 1, wetter than normal, versus the La Nina, drier than normal conditions. In this case, it still yielded above normal precip when it was combined, but it could go either way in this case because of destructive interference. Okay. Now, let's look at some of the MJO phases here. I will briefly show you. Now, I'm focused on December, January, and February, the winter season. This over here on the left is temperature composites. This over here on the right is the precipitation composites for December, January, and February. And you'll notice over here, I'm just going to pay attention to the left side of the temperature anomaly plot here. I'm really interested in December, January, and February, which months give me colder than normal conditions based on the MJO phase, and which composites or phases of MJO give me warmer than normal conditions. So blue represents below normal temps, orange represents above normal temps. And you'll notice here phases 8, 1, and 2 in the months of December, January, and February. MJO phases 8, 1, and 2 generally give me below normal temperatures for the eastern U.S., whereas phases 4, 5, and 6 give me the greatest warmer than normal anomalies for temperatures. See that? And then over here on the right, showing precip anomalies based on the MJO phase, a green indicating above normal, and then brown below normal. Phase 8 is here, showing above normal precipitation right along the Gulf Coast, right up towards the Mid-Atlantic. Phase 1, also very similar, green shading, above normal precip. Phase 2, generally kind of like drier than normal, further up towards New England, wetter than normal, Georgia to Florida. So you notice there's different phases that also favor, MJO phases that favor above or below normal precipitation. So just wanted to show you this. So now let's look at this phase space diagram, and these are readily available on the websites. You can go to the Climate Prediction Center website and just Google Climate Prediction Center. And you can get these phase space diagrams, okay? Now, what do we got going on here? Okay, we got all 8 phases that are noted here, the MJO. Phases 8 and 1 have convection in the Western Hemisphere and Africa. Phases, if the MJO is in phases 2 or 3, we have convection in the Indian Ocean. If we have phases 4 and 5 of the MJO, we have convection over the Maritime Continent or Australia. And then if we have MJO in phases 6 or 7, that convection or enhanced rainfall is going to be concentrated or focused in the Western Pacific Ocean. Now, this green line here is going to represent the average of all the ensemble members. And so let me just tell you what this small little inner circle here, this represents whenever the green line, the average of all the ensembles, whatever the forecast is, if it's within this inner smaller circle, that generally means I consider that to be the null phase or minimal impact to U.S. weather if it's in this small inner circle. The amplitude is much greater when this forecast line is further out away from the smaller inner circle. Now, one other thing I wanted to point out is in December, January, and February for the eastern U.S., the colder phases of the MJO are phases 8, 1, and 2. Whereas the warmer phases or the milder phases are going to be in phases 4, 5, and 6. So it's kind of like opposite of each other, right? So this would be the warmer side if the MJO forecast or the MJO is located in any of these phases over here, 4, 5, 6. It's milder than normal conditions for the eastern U.S. in the months of December, January, and February. If the MJO is over here in 8, 1, and 2, it's colder than normal temps for the eastern U.S. in December, January, and February. That's why it's so important to pay attention to the MJO. Now, the farther out from the small center circle, like I said, the greater the amplitude. So that means the stronger. When I say greater amplitude, that means the MJO is further out away from the small inner circle here at the center of the diagram. And that's going to have more significant effects on the pattern for the United States, the weather pattern. So now let's take a look and examine some of the past winter months. I took a look at various winters, just winter months in general. I tried to pick out some of the coldest winter months versus some of the mildest winter months. Here is an example of an MJO phase diagram, which we just went over on the last slide. Now, each of these color lines represents different months from October 1st, 1983 to the 31st of December, 1983. Okay, so for example, in this diagram on the left, MJO phase 8, well, basically blue line, let me just get you right on these months here first. The blue line represents the month of December and what the MJO did back in 1983. The green line represents November, and this red line represents October. Okay. All right, so initially what we had, look at this mean temperature anomaly or the temperature anomaly chart for December of 1983 here on the right. Look at the gray, this purple shading here indicate much below normal winter temperatures, and the green also indicates below normal temperatures. So much of the United States, green, blue, purple, and this magenta, all well below normal in December 1983. Now let's look at this. Where was our MJO in December of 1983? It's the blue line here. Okay. Basically, we had an MJO in phase 8 from the 7th to the 10th of February, and then back to phase 2 out here outside the small inner circle here from 18 to 25 December. Now realize too where this blue line is located in relation to this inner small circle. It got a little more amplitude, stronger amplitude out here in phases 7 in November, as well as phase 8 started working its way closer to the center of the diagram again. But in general, phase 8, 1, and 2, remember, they're associated with colder temperatures for the eastern U.S. when the enhanced rainfall is over the western hemisphere, Africa. Moving on to December 1984, that next year in December, it's a completely different story here. Look at the orange coloring indicating well above normal temperatures for the eastern U.S. All the cold stayed back in Montana, northern plains, back to the west coast. Look at the difference here, December 84, December 83. Impressive. And let's take a look at the MJO phase diagram over here on the left and see what happened. Where was the enhanced rainfall in that tropical Pacific area? In this case, again, the blue line is what I'm most interested in because it represents December. Really, I'm most interested in what the blue line is doing in all of the slides I show you, all the MJO phase diagrams I show you. But in general, in December of 1984, we were in a MJO milder phases 3 and 4, where the convection was in the Indian Ocean the enhanced rainfall and convection in the Indian Ocean initially, and it propagated eastward into the maritime continent over that location in Australia. So milder MJO phases 3 and 4 from 29 November right to 13 December, and then it came back out at the end of December 84 into the milder phase 6. So that matches up very well with what we'd expect. The milder conditions across the eastern U.S. in December of 84 match up with the MJO phase diagram. What about February of 88? Let's move it ahead. Now look at the amplitude on this particular MJO diagram here. The blue line again, well in this case, let's see, they do change up, I guess. Okay, now I'm taking you from January 1988 to March of 1988. So I changed things up on you a little bit. The blue line represents March. The green line here represents February, and then so the green line is February up here, the red line is January. And so you can see what happens here. In the month of February, this is February 88 over here, and look at the green coloring over the Midwest, much below normal temperatures, blue temperatures or blue coloring or colder than normal temps all the way to the East Coast down to Florida. Much of the area was below normal in February of 88, and it's no wonder why. Look where the MJO is heading. This blue line on March 1st goes into phase 1, 2, but then it goes into phase 3, 4, 5, and 6 by the end of March. Now, this is another thing I wanted to point out. Okay. In this particular February, where it was below normal for the East, the Midwest, and Eastern U.S., the MJO colder phase occurred at the end of February. This green line here, you see it's MJO phase 8. One important note is whenever this MJO rotates in specific phases, it's not an instant switch. It's not like a light switch in your house where you just flip it on and off. There's times where the MJO works its way into either a colder phase or a milder phase on this side of the diagram, and it might take 2 weeks before you start seeing the temperature anomalies reflect the phase. All right. December 1989, this was a very cold month for the eastern U.S. Look at the magenta and the purple coloring here from the Ohio Valley up to New England. And then it's no bargain if you're in this deeper purple coloring, because you're basically 12 to 13 degrees Fahrenheit below normal for the month of December 1989. And oh, by the way, those freezing temperatures went all the way to the Gulf Coast and South Texas. So not many people were spared. Florida, all the way down to Central Florida, you were down to 10 degrees Fahrenheit below normal for that month in December 89. I believe, if I remember my years correctly, I believe there were actually snowflakes that particular December in Disney World in Orlando. There were a couple snow flurries. Of course, that doesn't happen very often, but so what was going on with the MJO phase diagram? I'm going back to the October to December time frame here, 89 here on the left, the MJO phase diagram. Blue coloring again is the line I want you to pay attention to. That right there, the 1st of December, the MJO rotated into phase 8 with moderate amplitude, worked its way in, weakened in amplitude, worked its way in towards the center of the phase diagram, came back out 10 and 11 back in phase 8, went back in the smaller part, the center unit circle here, and then came back out into phases 2 and 3 by the end of December. But in general, you had a phase 8, which is going to be that colder phase, as well as phase 2, which is colder. And this was the result well below normal temperature anomalies. January of 1990, what in the world happened? December 89, the next month, January of 1990, okay? Very frigid start to the winter. And then January said, nope. I am just kidding. It's not going to be a cold winter after all. And look at how warm and above normal the temperatures were over the same locations that were shivering in December of 89. January 90, look at this. What was the MJO doing? This is January to March 1990 phase diagram on the left. Let's pay attention here. Let's see. So we're going to look for January. January color on this phase diagram is going to be red. So what happened in January? Well, this is totally explaining what happened. MJO started out in phase 3, and it amplified. The amplitude got stronger, further away from the center of the diagram. See this? See how far away this red line is as compared to the center of the phase diagram? That indicates we have stronger impacts or a greater amplitude to the MJO. So this red line is what I want you to pay attention to. We're rotating with great amplitude into phase 4. 5, 6. All right, that's all the milder phases for the eastern U.S. And look what happened as a result. Okay. December of 2000, now we're talking a well below normal temperature month again. Specifically the Midwest, where temperatures were on the order of 14 to 16 degrees Fahrenheit below normal in December of 2000 for southern Minnesota, Iowa, northern Missouri, and Illinois. Okay? And look at the cold that goes all the way to the East Coast and down to the Gulf Coast. The purple coloring here. You're talking temperatures 9 to 11 degrees Fahrenheit below normal for you in Virginia. Look at Florida, you're shivering. Look at Texas, you're shivering. The only place with above normal temps in December of 2000 was out in the desert Southwest in California. So what could cause this anomalously colder than normal temperatures? Let's look at the phase diagram, the MJO phase diagram over here on the left. We're going October to December on this MJO phase diagram, and I want you to pay attention, since we're looking at December anomalies here on the right, the temperatures, I want you to pay attention to the blue line in this particular diagram. So what did it do here in the month of December of the year 2000? It surprisingly started out into phase 5, was weak amplitude, then phase 6, phase 7, but then it did eventually work its way by mid-December into phase 8, the colder phase. And then it went back inside the smaller inner circle here towards the end of the month. And so very minimal impacts at that point. So there might have been some other teleconnection here as well that may have been impacting the pattern. It might have been the North Atlantic oscillation or the Arctic oscillation going strongly negative. It might have been the polar vortex and the stratosphere weakening drastically. Because I look at the MJO phase diagram over here, and it starts off actually in the milder phases, right? 5 and 6 in December. But then by the end of the month, it went to the colder phase. But it wasn't very strong amplitude. Looking at January of 2006 now. Look how warm everybody east of the Rocky Mountains was in January of 2006. Specifically, you that lived in the Ohio Valley, the Midwest, the upper Midwest here, Northern Plains. The brown shading here, 14 degrees Fahrenheit above normal in the Dakotas and eastern Montana, up to 18 degrees Fahrenheit above normal. That warmth went all the way to the Gulf Coast. And there's not much blue shading for January of 2006. Not much below normal readings as far as temperatures. What happened? Look at the red line here in the MJO phase diagram on the left. The MJO started out in cold phase 8, low amplitude, worked its way into the smaller inner circle here, and then it came out, and it came out with a vengeance in phase 5 and 6. Look how far the red line is from the center of the diagram. That indicates stronger amplitude. So stronger amplitude MJO in the milder phases, we have convection, enhanced rainfall generally concentrated over the equatorial areas of the Western Pacific, specifically over Australia, the maritime continent, and into the Western Pacific as a whole. Milder phases of the MJO from 15 to 29 January. And look at this result. February 2010, this was a frigid month for the eastern U.S., all the way down to you in the Gulf Coast, all the way to you in Florida. Look at the purple shading, look at the greens, blues, all below normal temperatures for February of 2010. Let's look at the January to March MJO composite here, the archive composite. Let's look for the February time frame. So look at the scale here. February is the green line here. The month started out over here in phase 7 with enhanced rainfall located there over the Western Pacific. And then we work our way into colder phase 8. See this? With some pretty significant amplitude away from the center here of the diagram. See this? 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So about 10 days in the month of February 2010 where we had the MJO in the colder phase 8 before it worked its way back into the smaller inner circle here. So by the time we got to March, the blue line, it came back out into phase 1, by the way. And so here's colder than normal temperatures. Now, some interesting things about the winter of 2009, 2010, we had a strongly negative Arctic oscillation. So there were some other things going on there in addition to the colder phase, the MJO. This could be a case of where you had constructive interference, where we had multiple phases working together. MJO phase 8, colder phase, plus a negative Arctic oscillation, or maybe plus a negative North Atlantic oscillation, okay? December of 2010, now this is an interesting month. Look, the purple coloring here, look at this on the right. well below normal temperatures for December 2010. This was one heck of a cold month. From the Ohio Valley, the Mid-Atlantic, down to the Southeast, and down to Florida. Not much in the way of warmth. All right. The MJO phase diagram over here on the left. Wait a minute. Let's look. This is from October to December 2010. Pay attention to the blue line here for December. What in the world? MJO started out in the small inner circle here, the center small circle, indicating very minimal impacts from the MJO. Then it worked out, the MJO worked into the maritime continent for enhanced rainfall. Still weak amplitude though. Weak amplitude, the MJO, into phase 4, 5, and then back to the small inner circle. So guess what? The MJO was not over here in the colder phases, 8, 1, and 2. It wasn't very far away. That blue line was not very far away from the center circle, the smaller circle here. So the MJO was not the reason you saw this on the right. What was the reason you saw this frigid blast of air across the Mid-Atlantic and Southeast down to Florida in December 2010? It was this. The AO index, the Arctic Oscillation, had crashed significantly negative. We had a stretch there of 2 back-to-back Decembers in which this Arctic Oscillation really went negative pretty strongly. December 2009, December 2010. And then look what happened in 2011 in December. The AO went solidly positive, very strongly positive. It's like it made up for time. It counteracted the negative winter Decembers with this. But anyway, this is an example here, the MJO. Just looking at the MJO alone is not going to give us this results. And so sometimes when you look at the MJO for a forecast, you can't necessarily just look at the one teleconnection, the MJO. You have to look to see what else is going on with the other teleconnections, whether we're talking Pacific North American pattern, whether we're talking this AO index or the NAO index, okay? So based on MJO in phases 4 and 5, east should have been milder than this. But we had a record-breaking Arctic Oscillation that was negative, and it overpowered this very weak MJO signal. Looking at February 2015, another frigid month for the East. You in New England were shivering your way through February of 2015. Cold air going all the way down to Florida again. It's almost as if you could draw a line right along the spine of the Rocky Mountains. Anything west of this line would be well above normal in the western U.S. and then well below normal to the east of that Rocky Mountain line. And what happened with the MJO, okay? This is February 2015. Let's go over here to the MJO phase diagram, phase space diagram over here on the left. Let's take a look at February 2015. Let's look at the coloring here. Green line is for February. All right, so the MJO small inner circle works its way into phase 8, the colder phase a little bit, kind of lingers around phase 8. Not very strong amplitude or strength. It's fairly close, this green line, to the small inner circle here. But then it works its way back into the inner circle by mid-February and then comes back out in 7. So this really doesn't indicate a very strongly cold phase of this MJO to give us this in February 2015. Again, there's other teleconnections to look at here. I would be examining what was going on with the stratospheric polar vortex in February 2015. If it was really weak and displaced off the pole, and then I had a negative NAO or a negative AO, this could be a result of that, okay? Did we have El Nino or La Nina that particular winter? Those are the kind of questions I would look at, because the February, this green line here, doesn't explain this. Now, the blue line, if this was March of 2015, and I saw the blue line representing March and what the MJO did in March, started in the center point of the phase space diagram, worked into 5, 6, phase 7, very strong in phase 7, and then very strong in phase 8 in March, and phase 1 as well. This definitely would make it a contributing factor to potentially colder temperatures in the east. Looking at December of 2015 now. Wow, it was a very mild time in the eastern U.S. in December 2015. I remember it well. This blue line explains it well. This is your MJO phase back in December of 2015. Look at it. It's in the milder phases, 4, 5, 6. Or enhanced convection or enhanced rainfall in the equatorial Pacific occurring over the maritime continent in 4 and 5, and then concentrated moving into the western Pacific here in phase 6 by the end of December of 2015. So this completely explains this. The MJO is in a very strong amplitude or strength well away from the center point of this phase space diagram into the warmer phases 4, 5, and 6. And this was a result in December of 2015. Looking at February 2018, another very mild month for the eastern U.S. Anywhere from Virginia southward, 7 to 10 degrees Fahrenheit above normal for February of 2018. The temperatures were well below normal across Montana that particular time period. Let's look at the MJO phase space diagram here on the left. Now, we're running January to March of 2018 over here with this MJO diagram. All right, so we'd expect the MJO in the month of February to be over here in 4, 5, and 6, the milder phases, right? The green line represents February, and what in the world's going on here? Okay, we have enhanced rainfall or convection over the western Pacific. Okay, got it. Phase 7 to start. Then it rotates into the colder phase, phase 8. Colder? Colder phase 8, colder phase 1 for February? What in the world caused this then? What in the world caused that? That's, again, I don't have the answer right there, but then again, I would look at the other teleconnections. Did we have a very strong stratospheric polar vortex in February 2018? Did we have a very strongly positive Arctic oscillation, a very strongly positive North Atlantic oscillation? I definitely could tell based on where these above normal readings are, we had a very strong upper level ridge. The southeast ridge was definitely a factor in this month, pumping in those warmer temperatures on its backside up the east coast. But again, you may not necessarily equate directly one-to-one of what the MJO was doing based on that particular month. There may be a lag in there, okay? January 2020, well above normal in the eastern U.S. that particular month, January 2020. And it matched up really well in this case with the MJO. Look at the red line here. The MJO was passing through the milder phases, 4, 5, and 6. See that? For the majority of January, and it was strong in amplitude. This thing was strong. Look how far away it is from the center of the diagram, this red line in January of 2020. And look at what you had as the results. December 2021, another very mild month, specifically Texas, Oklahoma, south central U.S., definitely 10 to 11 degrees Fahrenheit above normal, the brown shading here. But even the oranges go all the way up the east coast here in December of 2021. Not much blue or green on this particular month, indicating below normal temperatures, much of normal in December of 2021. What was the MJO doing over here on the left in December? Follow the blue line here. That would be phases 6, that's mild, and it's pretty good distance away from the center of this phase space diagram. So we have stronger amplitude in phase 6, we have stronger amplitude in phase 7. So that particular month featured convection or enhanced rainfall over the equatorial portions of the western Pacific. Okay, that convection didn't quite make it to the date line. That'd be phase 8. And that would indicate a turn to colder temperatures, and it just didn't make it that far. March of 2023. Okay, this is fairly recent. In this case, in March, we saw a very strongly negative phase of the MJO into phase 8 and 1, and then eventually into 2. Look how much further away, it's almost on the edge of this diagram, right, of this vertical line here. The blue line here is March. And look what happened here, though. Now, so you're saying to yourself, okay, beginning of March, the convection was focused in the western equatorial Pacific of phase 7. Then it propagated eastward towards the date line in the western Pacific. What in the world happened? Okay, so this MJO indicates that temperatures should be much colder, right? When the colder phase is 8 and 1. But why is it not the case? Look at this. We have orange coloring, which indicates slightly above normal temperatures for the mid-Atlantic and much of the eastern U.S. The coldest temperatures remain back over northern plains, North Dakota, Montana, Wyoming, Idaho, into Northern California and Nevada. Look at this. Salt Lake City, you're freezing. Colorado, the western portion, you're loving life because you're going to ski country and enjoying that beautiful, the slope conditions. But yeah, I mean, what happened earlier this year is we had an MJO turn to cold phase 8, colder phase 8 from 3 all the way to the 22nd of March. We'd expect below normal temperatures, but again, the MJO isn't like a light switch sometimes. It doesn't just flip on and off. It doesn't like just magically temperatures drop when this thing goes in MJO phase 8, for example. In fact, we had well below normal temperatures in May and June. Then there's a lot of other things going on in addition to this. We have the stratospheric warming event in February, and it took a little bit of time for those effects to be felt. Here is an example of some of the colder phases. I was kind of looking at different MJO phases over the years, specifically the decades. And I noticed, the blue line here in every case, here's a red line for January in this far right diagram. But in general, we saw more of the colder phases of the MJO in the late 1970s. Now, those were very frigid winters across the eastern U.S. So it's no coincidence that we have this kind of pattern going on in the late 1970s. So in conclusion for today's video, I want to make a major point here in bullet 1. I want to say that not all winter month temperature anomalies are going to match up instantaneously with what one would expect with a specific MJO phase. And sometimes they don't match up at all, especially if the amplitude or the strength of the MJO is not very strong. You can have other teleconnections such as the AO. We could talk about the North Atlantic Oscillation, the NAO, the PNA, Pacific North American Pattern. We could talk about the EPO, Eastern Pacific Oscillation. We could talk about El Nino or La Nina effects. Sometimes they overpower the MJO's effects on the atmospheric circulation and those long waves, the wave train that sets up, that the tropical convection, the up and down vertical motion, it tends to bleed into the mid-latitude circulation and creates more favorable areas for upper level ridges and anomalously warm temps, and then deep troughs and colder than normal temps. Phases 8, 1, and 2, however, when we looked at these winters, they matched up fairly well with what we'd expect, below normal temps across the eastern U.S. during the winter season. Specifically, we focused on December, January, and February. Now, phases 4, 5, and 6, they also matched up well with the milder phases above normal temps across the eastern U.S. during the months of December, January, and February. And again, we have to look at the amplitude or the strength. How far away are these lines in relation to the center of this phase space MJO diagram, okay? The further away these lines are, the stronger the impacts, and the stronger the amplitude. And when weaker in amplitude, the MJO usually did not have significant impacts on U.S. weather in the winter season, all the winters we looked at here in tonight's video. And again, emphasis on lag time. There's approximately a 2-week lag time from what we saw between specific MJO phases and then those temperature departures from normal. It was not an instant effect. By the way, for all you snow lovers for the winter season and that live in the east, snowfall over the eastern U.S. is generally going to be enhanced during MJO phases in 8 and 1. So MJO phases 8 and 1 in the winter season are going to give you higher probability of enhanced snowfall for the eastern U.S. Again, MJO is strongest during La Nina events, and we're coming up on an El Nino winter. Just keep that in mind. Why is it so strong during La Nina events? Because above normal sea surface temperature anomalies typically occur across the western Pacific during La Nina events. And whenever you got above normal water temperatures, usually enhance that convection, which also strengthens MJO, enhances that MJO strength when you have that convection firing up over the western Pacific over the above normal sea surface temperatures. The MJO is strongest, additionally, this is a nice little tidbit here, MJO is strongest during the easterly phase of the quasi-biennial oscillation, the QBO. And I'm going to go more into the QBO in a future video, so stay tuned for that. Here are the references from tonight's video. I took a look at the Madden-Julian Oscillation fact sheet, which you can find at this link. NOAA, National Centers for Environmental Prediction, as well as the NOAA Climate Prediction Center. I looked at the MJO archive, courtesy of the Australian Bureau of Meteorology. That was all these diagrams here on the left. I went back and looked at the archive database that the Australian Bureau of Meteorology has available. Also looked at this particular research paper, Deep Learning for Bias Correction of the MJO, H. Kim, Y.G. Ham, Y.S. Ju, and S.W. Sun. That was a paper published in Nature on 25 May 2021. And then I also looked at Hylene, the Madden-Julian Oscillation, this particular research article for this video. All right, that wraps things up tonight. I hope you enjoyed the video. We talked about the Madden-Julian Oscillation, some of its impacts on the temperature anomalies in the winter season, specifically the months of December, January, February for the United States. It's a complex thing, the MJO. But it's something you definitely have to consider each winter because of this, what happens here. How it alters the pattern, the atmospheric circulation, where the jet stream, the storm track sets up, and all these factors. You tie it in with other teleconnections such as NAO and AO, and it impacts a lot of people. All right, that wraps things up. I'm currently making a video on the differences between the central-based and the eastern-based El Nino, and what that means for winter weather in the United States. So I'm working on that one right now. I'm also planning to do the quasi-biennial oscillation, the QBO video, in addition to the central-based and eastern-based El Nino videos. Right, that wraps it up for now. Everybody, until next time, take care and God bless everyone.